Morning. I'm a computer science student at the University of California, Irvine. I'm a fourth year. Today I'll be presenting to you about the project I've been working on for the rescue robotics. We're working on an autonomous hovercraft that is capable of detecting victims and logging their positions and information about them, mainly their features. So the background. This project has been, the motivation for this project is a little different than some of the other projects. We're not trying to create a cutting edge technology. The motivation has come from a program called Performance Engineering Program that Professor McCarthy at the Department of Engineering is working on. The motivation for that program is to teach high school students how to write code and how to program. And the way that we're doing that is by giving them a task. That task is create a drone that's capable of flying by itself and detect victims. So that's the task that has been given to them. So the main work that we're doing is for creating a prototype that will be used for the competition. So create a framework for them to work on since they're beginners, and also to specify how the competition is going to be done. So how is the natural disaster environment going to be set up so that it simulates a natural occurring natural disaster. Okay, so our main goals, we have to create a prototype first. So our prototype has to fly by itself. It has to detect the victims and move towards them using some sort of sensor. It has to take pictures of the victims and label them. And it has also to log the positions and the victim information. And we also have to provide a learning environment for the students. So when you're thinking about solving the first problems, we also have to take into consideration that all that we're finding, all the solutions that we're coming up with, they will have to be done by the high school students as well. So that's a concern that we have when making the choices that we're making for creating the prototype. Okay, so technical work. For the hovercraft, what we had to do is we had to define the components for making the hovercraft. So we're creating from scratch. We're not buying a hovercraft and making it autonomous. We had to define the frame, the motors, the flight controllers, and all the minor components. We also had to come up with, decide the components that would be used for making the drone autonomous. What kind of sensor we're going to have. How we're going to be controlling the drone on top of the flight controller, since we're not using remote control for moving the drone around. And also, we had to define a solution for making autonomous. So how is it going to think? How it's going to decide its path? How it's going to see that the victim's a victim? And how it's going to, when is it going to choose to take a picture and log the position? So we have to define all those solutions, and we also had to write documentation for all of the above. And the kind of documentation that we had to write was basically for teaching the high school students, and also the instructors that will be teaching the high school students how to do it as well. So as we progressed, we had to create tutorials and provide workshops for the students on how to approach the problem. Okay, so this is an overview of our solution on the more technical side, getting a little specific here. We chose a flight controller that is widely available. It's not cutting edge, it's not the most stable flight controller that you can buy, but it is relatively cheap. It has a black box design, but it still allows us to control the input and output of the hovercraft independently. That way we have freedom on how we're gonna move it. It has geofencing, so one concern that we had was safety. When you're holding that competition for high school students, we don't want the drones to be flying around hitting people, so we had to find a solution that was safe enough for holding the competition. He also has a software for setting the flight controller. Some of the more sophisticated ones for cutting edge technology on drones don't have that. They don't have a nice guided user interface that you can just set up and tweak your your drone with. This solution has one, which is again our concern is to provide an environment where the high school students can thrive. We're using an Arduino Uno for controlling or making the flight autonomous. The reason why we chose Arduino Uno is because we provide an interface between the flight controller, and how it's making its choices. So instead of getting a flight controller that will just directly communicate with sensors, we're using the Arduino Uno in between. The reason why is because it has several libraries available for it. You can find online. So for high school students, they can just see those libraries online, and then they can easily program for it. It has a friendly programming environment. If you break your code, you're not gonna crash the quadcopter because you're having trouble running the code in the Arduino. So that you have that interface in the middle. There's a lot of modules available for it. So there's GPS, there's infrared sensors and whatnot. Some of the other microcontrollers available out there, the more powerful ones, they have very specific modules that only work for them. So when we started working with this, we didn't know which direction we headed towards, so we picked something that had the most variety of modules and sensors out there, so that we had freedom of choosing them. And most importantly, also we have host width modulated control. And what does this mean is that we are capable of simulating an RC controller from the Arduino that will be able to control the flight controller. I'll explain that a little more afterwards. So that's for flight. Now for detecting victims and logging. One problem that we have for detecting victims is how much computational power is required. Computer vision algorithms take a lot of memory, and they're really hard to compute. And when you're flying a drone, the overhead can be an issue because you're also having to compute all the variables for stabilizing the flight itself. So the solution that we picked was an embedded solution for doing object detection. Now, our victims are only, for now, barrels that have a specific color. So they don't really have faces. So if that was the issue, if that was our approach, then this solution wouldn't work. But for our solution, which is just again a simulated environment, this works. So we are using something called a pixie camera. It was developed at MIT. So the object detection is being done on the pixie camera itself. So it has its own processor for identifying color pixels, group them, and then place them as objects in the screen. So and it also communicates directly with Arduino. Again, simplicity and easy to use for the students. That's the reason why we picked that. And then we just have cameras and GPS modules for Arduino. Again, those are also easy to use. They are well documented. There's several sample codes online that the students can work with for retrieving the global position and also snapping pictures and just saving them in the SD card, which is how we are currently logging the information. We're just saving it all on an SD card, and for the competition, we're going to be extracting it afterwards, and then just making sure that the victims, the pictures that you took, match with global positions. That's our current approach. So that's how the logging is being done. We're taking pictures, we're saving the position where the picture was taken, and we're placing them in an SD card. We're just saving in memory to be looked at afterwards, which serves the purpose of identifying the victims because you have pictures of them and you know where they are. Now, this is the name, mainly on how our team is divided. I'm the team lead. I'm also working on the autonomous flight and on the victim detection, and I'm also providing these workshops. Already provided one workshop. Last quarter, we're providing one again, actually this weekend, the 21st. Another team member that has recently been added to our team is Zoe Chow, who cannot be here today. She is mainly creating a mode for switching between autonomous flight and RC control flight. And then we're also getting help from 2 graduate students at also the University of California, Irvine, who define the components for the actual quadcopter. Not making it autonomous, but just the flying structure. Okay, I don't know if you can see that, but this is the list. This is the list with all the parts that we have for the quadcopter right now. So each quadcopter comes to about $1,000. For the budget for our project, actually, since we were holding this competition, we actually had help. We were sponsored by Vitalink, and they bought 10 kits of this for holding competitions. We'll be going to be holding them annually for now on, I believe, for the pharmacy engineering program that we're working with. But this is roughly the price for each drone, which is relatively cheap. And it is capable of doing all the victim detection that you normally have. Some of the more sophisticated drones, they're way more expensive than that, just the drone itself. So that's something that we're proud of, because since that we're doing it all from our end and not getting any solution that has already been provided before, and we're not using expensive modules or expensive microcontrollers, it came up to be relatively cheap. Okay, so this is what we've done so far. We've been able to control the drone autonomously, which was a challenge. I'm going to talk about this in a little while. We've also done the victim detection, so we're using the PIX camera for identifying the victims and seeing where they are in relation to the drone. And we also already provided one workshop, as I said before. So this is what I've done so far. This is what we're doing right now. We're figuring out the victim logging. So how you snap the pictures and how you save them, and how you save the global position for the victims while you're doing the flight. We also created this device that switches between autonomous control and remote control remotely. So if anything is going wrong, you can just flick the switch and it's going to go from autonomous to remote control, and you can save your drone if it's about to crash. And then for teaching, we are also providing another workshop for teaching how the victim login and how to create a circuit for changing the remote control remotely. And future work, something that we've not been successful so far was providing a way for wirelessly reporting the victims. It was very unreliable for the competition we have right now. We also needed to create an application just for receiving the data that will be sent by the drone and safely put the data together. And the pictures was, it will be challenging, especially because we're dealing with network solutions, and our focus right now is just creating a working drone and teach the students how to do it. So that would be an extra, that would be an overhead in our project, I could say, because it's not of importance. But in the future, we want to do this just because it's more elegant to have a drone that's providing information wirelessly. This is the main innovation that we had, and this is what I was talking about earlier: controlling the flight controller or controlling the drone using an Arduino. The way we're doing this is by simulating a remote control from the Arduino. So remote control uses this method of communication called pulse width modulation. They're basically square waves. I'm not going to get into detail like how the science works here, but by providing a simulated RC controller, we can harvest all the computational power that the flight controllers that are in the market use for stabilizing the flight. If you try controlling a drone by just saying move forward or to the right or to the left, it's not going to have a stable flight. But a lot of the flight controllers, actually all the flight controllers, they compensate for human error, or they make the flight more stable if you're flying with a remote control. So it can harvest all that computational power that's being done to make the flight stable provide a safe environment where you can also control it autonomously. So that was an approach that we had to think of. That was a little out of the box. Initially, we were planning on just controlling it from inside the flight controller, but we realized that there's a lot of computation being done for keeping the flight stable. And if you try just moving the drone by saying move right or move left directly from the flight controller, that can lead to issues. Mainly, you'll crash. So yeah, that's it. Any questions?